Thank you, thank you. Yeah, my name is Kieran. I'm working on OpenVZ, and this is what I'm going to talk about. Since it's my first time at FOSDEM and in Brussels, it's a pretty generic introductory talk, but there will be some features that I especially like to talk about. So the agenda for this talk is, first of all, we'll see different virtualization approaches, and when we'll talk about containers in particular, and OpenVZ and its components and kernel stuff. When I'll have some performance slides for you, and I'll end up talking about a few new features we are currently working on. So, basically, in context of this talk, virtualization is a technique that lets you divide one big piece of hardware into multiple smaller ones. So this is basically partitioning. You partition a big system into smaller ones. And there are a few ways to do that. First of all, there's a hardware emulation, which is also virtualization, actually. So you can emulate a CPU and run anything on top of that, or emulate the whole system. Then there's virtualization, which is like Xen or KVM or VMware is doing. Then there are containers, which is what I'm doing. And finally, there is multi-server virtualization, which is out of the context for this talk, but it's when you do something opposite. You combine multiple pieces of hardware into one super piece, and then you break it into smaller ones. But this is out of the context. So with virtualization, what those guys do is they have on top of hardware, they have a layer called hypervisor or virtual machine monitor, which lets it create multiple instances of virtual hardware. And on top of that instances, you run your operating systems. So this is what Xen, KVM, VMware, and other guys do. Opposed to that, what we do is we modify the operating system kernel. In our case, it's Linux kernel, to provide multiple instances of the user space, which we call containers. And it's not just OpenVZ, there's also LXC. Well, FreeBSD jails is kind of precursor to the containers. It's not a full solution, but it's there. When Solaris zones, and there is also in AIX6, they have workload partitions, which are basically containers too. So these are all container solutions. So the comparison between hypervisors and containers is, with hypervisor, you have multiple pieces of virtual hardware, and you can roll multiple operating systems. That means you can run different operating systems, Windows, Linux, whatever. But it also means you have lower density, and by density, here I mean how many such VMs can you have on the particular piece of hardware. And you have to pay some performance penalty, and there are some scalability problems, like one VM cannot have all the 64 CPUs that you have on your systems. And actually, those lower density performance and scalability in case of hypervisors, they've been thought by hardware vendors like Intel and AMD. They're introducing features to help hypervisors cut the corners here and there. So those performance problems are being mitigated and dealt with. As opposed to hypervisors, with containers we still have one piece of hardware, and one kernel, not multiple kernels, but just one kernel. And on top of that, multiple user spaces. What this means is we cannot run any other operating systems. So it's the Linux kernel, so it's Linux user space. But this also means that we do it much more effectively. That is, much higher density, so you can have more of those containers that you could have VMs. That means native performance, pretty much no performance overhead. I mean, you could have hard time measuring the overhead in this case. And as an added bonus, it's dynamic resource allocation in terms of like memory, for example. You can give containers more memory, less memory, and you can do it all during runtime. So personally, I consider this as the containers as a natural step in operating system evolution. We have multitask operating systems, we have multi-user operating systems, and now we have multi-container, multi-user space operating systems. I mean, if you think about it a bit, it's pretty obvious idea. So let's go and see what OpenVZ consists of. Of course, most of the stuff is in the kernel, and it's the kernel which provides the ability to have many containers on top of it. And the means that kernel uses to do that are, first of all, namespaces that provides virtualization and isolation between those containers. Then there is a cgroups, which is resource management control mechanism. And then there is a checkpoint restart. It's actually an auxiliary feature, but it's pretty big, so I put it on his own. That means that you can freeze the container and unfreeze it later. It's like hibernation for your notebook, but just for container. Then there are some tools and what we call templates. Basically, these are pre-created images that are used for fast container provisioning, images of different Linux distros, which you can use as a base for containers. So let's take a deeper look into the kernel part. Each container, from the point of view of container's owner, it's a separate entity. It has its own files. It has its own processes, own network device with all the, IP tables, firewall rules, and routing rules, metrics. Each container has its own devices, and all the other stuff that kernel provides, for example, IPC, inter-process communications, which is shared memory, semaphores, and messages. Each container has its own set of IPC objects, so they don't interfere with each other. And that stuff is done using so-called namespaces. And the easiest and historically the first namespace is chroot system call. If you know what it does is it makes some directory on the system your new root, so you cannot go up there. So actually chroot is a precursor to the containers. It's a file system namespace. It lets you see just some subset of the files, not all of them. So if we take this chroot idea and apply it to everything else that kernel provides to programs, we have containers. So chroot is a file system namespace. Then we have a process ID namespace, so the container only sees its own processes. We have network namespace, IPC namespace, and so on and so forth. So this is how we provide isolation between containers. But that's not all of it. The problem is there is one kernel and one set of resources like memory, disk, and so on. So there is a need for a resource management mechanism to keep the containers within the limits, the ones that we set, in terms of memory, CPU, disk space, network, and so on. So we have 4 mechanisms in OpenVZ. First one is historically called user bean counters, which is it's a set of 20 resource control parameters, mostly memory related, but there are some auxiliary ones like number of open files, number of processes that you can have in containers. So for each container, there is that set of limits. Second thing is fair CPU scheduler, because usual CPU scheduler, it schedules the CPU between tasks. So it just takes the task from a run queue and give it a CPU time slice. And this would not be fair because different containers, they have different amount of processes. So we have to schedule between containers first. So we pick the container to give a CPU time slice to, and then we pick a task within that container. And that way we can achieve fair CPU distribution between containers. Of course, there are weights for each container, so you can have high priority, low priority containers in terms of CPU. And there are hard limits, like no more than 10% CPU time, no matter what. Yet another mechanism is two-level disk quota. Because container file system is a directory on the host system, we have to limit that space. So we have per container disk quota per directory. And inside the container, the user can use usual Linux quotas. And finally, there is a disk I/O priority. So it's a common disk, many containers, they can affect each other in a bad way. So you can isolate the bad guys by giving them low I/O priority. And the fifth item here would be networking, but it's pretty much solved without us. There's a nice tool called TC, which gives you ability to have QoS, traffic shaping, and all the other fancy stuff with networking, to control networking resource. Now, third thing is checkpoint and migration. As I said before, that means that container can be frozen and dumped into a file on disk. The complete state of container, all the running processes, open files, network connections, memory segment, buffers, whatever. And at a later stage, we can restore it from the file back to memory and restart it, so it will continue to run. And the nice thing about that is we can restore that on a different system. So we freeze the container, checkpoint it, move the dump file to a different box, and then we restore container on a different system. That is called live migration. So you can migrate containers between two boxes, and I'm usually demoing it on using two notebooks. So, I mean, unlike the same solution from VMware, there is no need for any fancy hardware for that. You can do it with any two OpenVZ boxes. So that was all about the kernel. Just one slide about tools. It's a high-level, VZCTL is a high-level tools to operate with containers. Here is, which you can see typical container lifecycle. We create the container, specify the distro, use that template I was talking about. When we set the IP address, the same way you can set other parameters like memory. When we start the container, go inside, see that there is a usual set of processes inside, usual process tree. When we can stop it and destroy it. And all of these, you can do it in about 2 minutes. Compare that to time that you need to set up a physical server. I mean, whenever you need something, even whenever you need a new server, you can fire up a new container in 2 minutes. So, a few interesting performance slides. This slide is showing LAMP throughput. LAMP is Linux, Apache, MySQL, and PHP, right? So this is a DVD store test done by Dell that emulates a big web store selling DVDs. And what we did, we run 20, 40, and 60 containers and VMs, and we compare how many requests per second can they do. The rightmost bars, the red ones, are OpenVZ ones. As you can see, it's more scalable. If you look at 20, then 40, then 60, all the hypervisors are going down on 60. That means they reach their density limit. There's no more ability, hardware ability to have that many kinds of VMs. And in OpenVZ, it's still growing. That graph, except for that it shows that containers are more fast, it also shows that they are more dense. And the next slide is the same test, but we see the response time. So the lower, the better. And the others are VMware ES6, Hyper-V, and Xen servers. Sorry guys, no KVM here. The next slide is vConsolidate. It's a benchmark by Intel that is used to measure consolidate workload. It runs some heavy Java apps inside VMs. And those VMs are grouped into so-called CSUs. So we have the case for 1 CSU, 5 CSUs, and 10 CSUs. And the two last items, orange and red, are OpenVZ, just different kernels. Orange one is the kernel based on RHEL 5, and the red one is the kernel that is based on RHEL 6. Which is better in terms of SMP scalability. They fixed a few locks and contentions. So again, you can see that it performs better. And I would like to show a slide that shows that containers are worse, but I was not able to find such a test. So that's enough for performance. And if you want to see more of that stuff and detailed descriptions of the test cases, it's available on our wiki. The page is called Performance. Now I want to tell about a few features we've been working on recently. First feature is called vSwap or virtual swap. So then I was telling about the resource management and those user bin counters. There are 20 parameters, and the good thing is that you have a lot of configure, and the bad thing is you have a lot to configure. Just because those 20 parameters, some of them are interdependent, and you can come up with the invalid configuration if you are not careful. And it's a bit complicated to manage. So we thought out, and our latest kernel comes with this feature called vSwap, which is the answer to user encounters configuration problem. Now you only have two parameters, RAM and swap. So for each container, you can say 1 gigabyte of RAM, 2 gigabytes of swap. And the thing is that swap is not real, it's virtual. What happens if the container is over its RAM limit, the kernel moves some pages out to swap, but not to the real disk swap, to some virtual swap. Actually, it's a swap cache. And then it slows down the container artificially to emulate the effect of swapping. So if you're over your RAM limit, you will be penalized. You will feel that you are swapping, but no actual disk I/O occurs. And then, if there is a real global RAM shortage, that virtual swap actually goes out to disk to a real swap. This feature is pretty complicated, and it took us like 3 years to put it into production, but now it's working very good, and it's in the stable kernel, and we recommend everyone to use it. Next feature, I was actually doing a presentation about this feature alone. I mean, I can talk for hours about that, but I tried down to have it just in one slide. And the feature is called ploop, or the other name for that is container in a file. Remember, I was telling that container is a directory on the host system, so all the containers files are actually the host system files, just a subdirectory of it. This is the way they usually worked, but what VM guys do, they usually have one big file, and inside this file, the whole VM lives, its file system lives. And we found out that in some scenarios, it is good to have everything in one big file. It's easier for backups, it's easier for migration, and there are some other scenarios. Scenarios like if you want to migrate container inside a virtual, like transfer a container into the real virtual machine or back. It's good that you have it in one big file. So for that, we kind of re-implemented Linux loop device, but we did it in a modular fashion. So it's not let's say it's not a stupid loop device, but an intelligent one that understands different file formats, like those expandable formats. Like you have 4 gigabytes inside the container, but outside it's only the size of the file is the size of the actual files. And when more space is needed, the file grows. For that, we need to keep in mind the mapping between the inside blocks and the on-file blocks. So there is a model that supports that transition, and you can have different formats, like the one used by KVM and QEM and so on. Then on the lower level, there is an I/O module which can talk to file system, which can talk to the VFS layer, meaning any file system, or which can talk directly to the NFS server to cut the corners here and there and make it, more performance-wise. And one interesting feature about this is you can have a few images layered on top of each other. So I was talking about just one image file, but you can add another one on top of that, make the lower level read-only, make the upper one read-write, and this way you can create an instant snapshot of your container. So the lower level is read-only, and this is the state of the container file system at the moment that you make the mount. And this feature is not upstream yet, but we hope we'll be able to merge it into the Linux kernel. And finally, yet another slide that I'd rather have a full presentation on is our newest project. It's called Crew. Then I was talking about checkpoint restore. Then you checkpoint container and restore it on a different box. This is all done in the kernel. And it's pretty complicated, advanced stuff. It is rocket science. And it has to know everything about processes in the kernel, their resources, the way they interact. And therefore, it's a lot of complicated kernel code. And we tried to merge it upstream a few times, and every time we tried, we failed. When we decided, well, let's keep it off the main line, and then there was other guy called Oren Laden who spent like 3 years of his precious time trying to merge the checkpoint restore functionality in the main line, and he failed too. So we decided that the only solution of putting it into the kernel is not putting it into the kernel. We're trying to do it from the user space. All the complex logic is in user space, and we still need something from the kernel, but we can cope with some minimal changes like export a few pieces of information that we need through the proc files, or letting us do something that usually user space is not interested in doing. And therefore, it's a huge user space project and some minimal kernel interaction. And I'm very happy to say that Andrew and Linus it was about a month ago, they accepted the first pile of kernel patches from us with the following command. This is a project by various mad Russians to perform CR mainly from user space. And Andrew is actually pretty positive about this thing, as you can see in this comment, because, you know, they all saw unsuccessful attempts to merge it, and this project, if it will end up, you know, in working state, it will do the same as a lot of people want checkpoint restore, and this is the only way to have it in the kernel, I guess. So that's pretty much it. What we have is platform. Well, actually, I forgot to tell about it. Unlike hypervisors, which are very platform dependent, they have to know everything about processor architecture and so on. Containers are platform agnostic solution. So OpenVZ works on Intel, ARM, MIPS, Spark, and I'm not a kernel developer myself, but when I got some ARM board as a present, I just decided, why don't I port OpenVZ to that thing? And I did it in like 3 days. So it's platform independent. So there is no problem supporting other architectures. And there are no problems with scalability or disk I/O that hypervisors suffer from. That means that if you have a huge server with, I don't know, 1,000 CPUs and a terabyte of memory, you can assign it to one container, and your container can use all of those resources. There are no limits like 4 gigabytes of RAM per container or no more than 4 CPUs. And you have the best possible performance, pretty much the same performance as usual Linux system gives you. And finally, since it's done on the different level, it plays well with others. What I mean here is you can use Xen and OpenVZ on the same box, or KVM and OpenVZ on the same box. So you can have lightweight containers, and you can have full-scale VMs. So best of both worlds. That's it for today. Any questions? Over there. So there's a microphone in here, so it's better if you use it. Unfortunately, it's not wireless.
I'm interested in checkpoint and restore in user space, and I was thinking that is it possible to integrate it with in the future with LXC, the Linux container in the kernel?
Yeah, I mean, when checkpointing will be in the main line, it will be used by any software. So LXC will get it automatically, the same way LXC got process ID namespace and network namespace from us.
So it means in the future LXC will be able to do live migration?
Yeah, I mean, currently, speaking about LXC, I actually have a backup slide in here. I was expecting this question. What I really want to say is it's not like OpenVZ versus LXC. What I want to explain is OpenVZ is a project, historically we had it off the main line and we are working on it for more than 10 years already, and it was off the main line. But 7 years ago we realized it's a bad thing to do and we need to merge upstream. And we started that effort 7 years ago, and we are working on that, we're still working on that, merging bits and pieces of containers functionality into the mainline Linux kernel. And the last time I saw there was about 1,500 patches from us in the mainline kernel. This is mostly namespaces and various cgroup controllers. And we are still working on that, and those ploop and vswap and the crew is all going to be in the mainline. We are very actively working on that. And when we merge something mainline, we use it from the mainline and we drop our own code. This code is also used by LXC, right? And so it's not one versus another. It's just like an ecosystem, like a symbiosis, I don't know. But currently the difference is OpenVZ is very stable, it's in production, has lots of users, and LXC is more like a work in progress. And currently it's not a ready replacement for OpenVZ. But we hope that in the future we'll have everything in the main line, so OpenVZ will probably become a set of user space tools. But, you know, the stuff that we merged so far, it took us 7 years. I'm not sure how many more years we need to push the rest of it upstream. So that's the thing about LXC. Any questions? Any other questions?
We have a lot of time. So, Mike.
Yeah. Hello. I'm interested to execute a graphical program within a container. How can I do it? Graphical program. For example, I want to sandbox in, Firefox, for example, or some graphical program.
Yeah, you can do that.
Possible?
Yeah, right. Well, currently X server requires direct access to the hardware, so you cannot run it inside a container unless you make the container really insecure, give it access to /dev/mem and other nasty stuff. So, but there is a way. You run so-called XVNC server, which is a virtual X server. You run it inside a container, and you connect to that server using VNC client. It's like our desktop. And that way you can run Firefox inside a container and all sorts of GUIs, GUI apps. We have a page about that, and it's called wiki.openvz.org/x inside CT. CT is a container. So it's all explained there. I just tried it 2 weeks ago, and it works. I mean, last time I tried it was 2 weeks ago.
Now, what are the contributions done by IBM for LXC and the parallels for OpenVZ? Is there true support to this project?
IBM, well, I had a slide on that, but it's not here. What IBM was actually doing, okay, let me tell you a big story. About 10 years ago, they acquired a French company called Meiosis. They had a project called MetaCluster, which was actually sort of containers. They had containers in order to run Oracle and in order to migrate Oracle. So they had containers for checkpoint restore capability. And then IBM acquired that company. The end result is they have containers in AIX, and they also tried to work in checkpoint restore front, but as I said before, all the attempts failed to merge anything. So the contributions from IBM is, if I remember right, it's in the resource management stuff. Well, they also had a project similar to our user bin counters, or similar to cgroups and resource controllers. It was called CKRM, and it failed to merge into the mainline, and that project is now dead. So historically, they did a lot of that, but not all of that stuff became accepted into the mainline. What was accepted, if I remember correctly, is some stuff with resource management, cgroup controllers. We were working together with IBM guys on that. And also, the guy who maintains LXC user space tools is a Red Hat employee.
Hello, yeah. Coming back on LXC versus OpenVZ, am I right in thinking that LXC is then less stable and a less good option than using OpenVZ at the moment? Or is it more feature-wise?
Well, LXC is kind of re-implementation of OpenVZ in the mainline. So
it is lagging behind, right?
In terms of features, yes.
And in terms of stability?
Yes.
Also, okay.
Yeah.
Okay.
So, I mean, I don't want to say bad things about LXC, but it's a very young project, and it's not as stable and, you know, as OpenVZ, because we have 12 years behind us, and that shows in stability and features too. Anyone else?
There are two approaches in terms of networking virtualization,
Right.
Through going bridging and
routing.
VNet. And I've read a lot of things about the difficulty in order to get secure environment through virtual bridges. Will there be more documented pages on the wiki in order to have a better approach, mainly for IPv6 to manage bridges issues in terms of security? Because plenty of people want to use bridges to gain this performance in terms of latency, to do telephony through containers. And do you know if there are works in order to have an advanced level of support in IPv6 through bridges?
Yeah, I mean, IPv6 works fine with both VNet and vEthernet, but you are right that it's not as good documented as it should be. I take this as a bug report. Okay?
Yeah, okay, thank you.
Over there.
Are there plans to support SE Linux or
SE Linux? Well, once we supported UpArmor, which is Novell's implementation of SE Linux, but it was easier because UpArmor architecture is easier. What we think about SE Linux is that it's a security model, and containers is another security model. And whenever you need that privilege separation, you just have a separate container and run anything in a separate container. So this is how we approach it. But I mean, if it will be a serious push towards adding SE Linux support, we'll have to do it. But for now, we haven't really seen great demand in that. I mean, because, yeah, SE Linux is making walls between applications, and we are making walls between applications too. So you can use our walls if you need that, right? All right. Thank you very much. Yeah?
Could you comment on the security-wise, the separation between the containers, like suppose in a shared hosting environment or something?
Yeah,
like
right. The thing is, OpenVZ and its commercial counterpart, the product based on OpenVZ, it's used by, I don't know, 80–90% of all the hosting service providers. And they sell those cheap VPSs for like 10 euros a month, and you have root access. So if it would be insecure, all these guys, all the huge guys like 1&1, Host Europe, they would go out of business very soon. And this is a practical, answer to your question. It is secure because people are using it. I mean, actually, this is one answer, right? The other answer is we did a security audit of our code by a very good security expert, Solar Designer, and we hired him to do that security audit. And he found 3 bugs in the mainline code, not our bugs, security bugs, and 1 minor bug in our code, which we fixed, and we fixed all those 3 too. But so theoretically, it is secure too. Practically, it is secure. And the security is mostly coming from, it's mostly coming from constant care. It's more like a process. Security is not something that you have for granted. You have to think about it. You have to be aware about all the possible concerns. and so on. And since most of our customers in the host and service provider business, we take security very, very seriously.
I see. And would there be a difference with LXC then? Or?
Sorry?
Would there be a difference between LXC versus OpenVZ security-wise?
I really can't comment on LXC security at the moment. I mean, you know, aside from development of OpenVZ, we do a lot of in-house testing. We have a huge farm, we have a big team of QA engineers, and we do a lot of automated testing for OpenVZ. And I'm not sure if someone is doing that for LXC. So it needs to be tested a lot before it, you know, before you can say that it is stable and secure.
Just.
Hello, just one question. If I buy some chip with $10 VPS, it might be run by OpenVZ. Can I run OpenVZ in it? In
No.
short, can I run OpenVZ on top of OpenVZ and so on?
You can do that with hypervisors because they create virtual hardware, right? But we don't do any emulation, and it's only one kernel.
Okay.
And you cannot run OpenVZ inside OpenVZ. So this is the short answer, okay? And the long answer is, theoretically, you can have nested namespaces, a namespace inside a namespace inside a namespace. But we played with it a bit, so you can create, you know, sub-containers within your container. We played with it, and we found out that it brings bad performance penalties. So we gave up this idea, and we think that flat hierarchy of containers is better in terms of performance. But some of the namespaces, for example, process ID namespace is actually nested, so you can have process groups inside your container which are not visible to each other. I mean, that could be done, but we think it's not practical to do that.
Hello, and what about support of systemd? Or how could you estimate the plan of implementation?
Actually, we have it running with a few patches. It needs some support from cgroups, so we are getting there actually. And
so you also
I can tell you that Fedora 16 with systemd patched by us, there are a few patches. It runs fine. So
Okay.
it's already done. We just need to send those patches upstream. I guess.
Thank you.
All right. Thank you very much.